Okay, moving on now. We've defined student's t distribution in terms of this interesting improper integral, as well as a multiplicative constant out front. And before we move on, we're going to need to briefly touch up on a definition, the definition of what's called the gamma distribution. That will help us to solve this improper integral. So this is a bit of an aside. And we'll need to know about the gamma distribution. Now the gamma distribution is defined to be this beta raised to the eta x eta minus 1 times e to the negative beta times x all over gamma of eta. Okay, so this is just another probability distribution you might encounter, and knowing about this distribution will help us resolve that improper integral into a more manageable form in the future. And we also know other properties about this integral, particularly the cumulative distribution function of the integral, which has this convenient expression. Now this is what's called the lower incomplete gamma function, and that's the numerator, and the denominator is simply the gamma function with respect to eta, excuse me. And one salient feature about the lower incomplete gamma function is that in the limit, as x goes to infinity, the lower incomplete gamma function simply becomes gamma of eta, irrespective of eta and beta. And those facts and features are going to help us resolve that improper integral above. Okay, so I'm just going to draw a quick dividing line. Now, this is a bit of some magic, just choosing the right substitutions given our definitions, given various identities. We task ourselves with solving the following improper integral. Some pretty basic calculus. And we're going to start by making some substitutions. First off, we're going to define m, and m is going to be equal to x squared, which means dm, the infinitesimal m, is going to equal 2x dx, which simply follows from the definition of the derivative of m with respect to x, which implies rather obviously that dx is equal to dm over 2x. And further, that x is defined in terms of m as m raised to the 1/2 power, or the square root of m. Making these substitutions, we're going to get another integral, and I'll just copy this to save myself some time again. Making these substitutions, we're going to get a new integral, which is equivalent where we have this definition, and here's where the definition for our gamma function, the gamma distribution, comes into play with our definition. We can judiciously choose new terms, and I'm just doing this for explication, to define a particular gamma distribution in terms of k and theta as m to the k minus 1 e to the negative m over theta of theta to the k times gamma of k. Now we're going to match coefficients between the integrand and the probability density function of our new gamma distribution that we just defined. So I'll do that here. We're going to match coefficients, which means if we look at our integrand and we look at our newly defined gamma distribution, we can match these coefficients. It looks like k minus 1 sort of associated to our v over 2, and then in that sense, maybe we'll define a new value, recalling the definition of v is related to n. We'll get this value, and our 1 over theta seems to be associated with this value, and we can define a new theta star as this. And now we're going to normalize the integrand, and we're going to do that by multiplying a judiciously chosen constant. Again, a lot of this is by ansatz and just figuring it out, utilizing a bit of foresight, looking at the problem from its conclusion and working backwards to pick the right terms, etc. But again, it all works out. So now we need a normalizing constant. And we're going to multiply that integral by a normalizing constant. This normalizing constant is theta star to raised to the k star times gamma of k star. And if we multiply the integral and divide the integrand, that allows us to write this, which will be intuitive sort of once we get to the end here. All over this normalizing constant. Again, the reason why we do this is because we're trying to essentially resolve the integral without actually having to resolve the integral as it was given to us. We're transforming it. And what we notice is that integral from 0 to infinity is simply equal to 1. It's simply 1. And that follows from the definition of the gamma distribution, and it's 1 times our multiplying our normalizing constant. Now, we can, from here, we can show that what we created with our integral is in fact nothing other than the integral of a gamma distribution. Why is that? Because this integral from 0 to infinity of this integrand that we had here if we replace the denominator with our definition, with the definitions of each of these terms, we get this value, which, if we recall from our definition of what it means to be a gamma distribution, this is nothing other than the gamma distribution of M with these terms, where eta equals n plus 1 over 2, and then beta is 1/2 n plus t squared dm. Now, if we recall the definition for the cumulative distribution function of a gamma distribution, we get this nice formula. Just choose the upper limit of integration to be a, and we get this. Again, just writing this out. I know it's a waste of time, but it's pleasant. So we recall that this is related to the lower incomplete gamma function because it's the cumulative distribution function for a gamma distribution all over gamma of n plus 1 over 2, where the limit as our a goes to infinity of this term is equal to gamma of n plus 1 over 2 all over gamma of n plus 1 over 2, which is equal to 1. And so that's a nice result. We definitely chose the right constants in that regard. And we did that on purpose, obviously. But still further, we need to discern the student t distribution. So if we recall that we were trying to solve for that integral, but we had that multiplicative constant out front, so I'm simply going to rewrite the constant. And here we go. And recall this is the solution to that integral. Simplifying, we get that this is merely 1/2 times 2 1b squared over 2 times and we recall that multiplicative, that normalizing constant had this form, and that we can simplify this further because this term here, this term, right, we notice that we have a term here that merely equals this. Just notice that I'm not writing out the full expression, but merely a term of the expression, and you can check my algebra. And if we write this out in full, we get 1/2 times gamma of v plus 1 over 2 over gamma v over 2 times, we've got a 2 here, and we've got a 2 here, and then the square root of 2 pi term, have v times v squared, or v raised to the v over 2 power. We also have v 2. I'm simply writing this out in full, and then I'm going to cancel terms later to arrive at a fairly nice definition for students' t distribution, which you'll be able to check the relevant literature if you want. And then we notice we can make some cancellations. The 2 cancels. This term here cancels. This term here will cancel with this 2. We also get that this v here will cancel with this. And that allows us to arrive at a definition for the student t distribution function, which has this nice form, which we'll use in the next section. Has this nice form. Right here. And one can check that this is in fact the probability density function for the t statistic. Okay, thank you.